We have Noam Shazeer. He spent 21 years at Google. He was involved in the famous Transformers paper from 2017, was involved with TensorFlow. Noam, you're a legend in this field. Thank you for joining us.
It's really a very experimental science. It's a lot like I would imagine like chemistry was in the days of alchemy.
I think there is going to be an existential question over the next few years about what data is this trained on.
You can just talk to these models and it's the coolest thing ever.
Why can't you consistently build out these incredible probabilistic models where it always picks the next right word?
We called it Phil. We figured it would one day turn into AI and we wanted it to sound non-threatening.
You said nobody really knows what's happening inside these models.
We turned it into the first targeting function for AdSense, which ended up making a lot of money.
It's quite the treat to have one of the authors of this paper to come and explain to us what attention and self-attention means. It's such a rare privilege.
Hey everyone, we have a special episode for you. We have Noam Shazeer, and Noam has such a fantastic resume and background that I want to make sure I read this out. Noam is currently the founder and CEO of Character.AI, but before this, he spent 21 years, if my math is right, at Google.
I left a few years in the middle, but I was mostly there.
Okay, quite a long period of time at Google. Just to put it simply, Noam has probably been at the heart or has been responsible for a lot of the research and development work that has gone into large language models today. So just some examples, he was involved in the famous Transformers paper from 2017, which you're going to really get into, with sparsely gated mixture of experts in 2016, was involved with TensorFlow, was a major contributor to Google's LaMDA dialog system. The list goes on and on. Noam, you're a legend in this field. This is such a delight. Thank you for joining us today.
Thank you, Noam.
Oh, thanks for having me on.
Okay, so we're going to get to AI in just a bit, but I want to ask you about a fun story. I don't know whether it's true or not, so you got to tell us whether it's true or not. When I was Googling you and preparing for this conversation, I was looking at Hacker News, and there is a story about you on Hacker News, which says that when you joined Google and you were originally interviewed, one of the answers you came up in the interview actually wound up being something that, Gmail wound up using later. So I don't know whether it's true or not, but I'm curious to kind of hear your history about how did you wind up in Google and the story ever since.
Let's see. I went to Duke for undergrad on like a math scholarship. Okay. Not basketball. I got injured. No joking. But there was a math professor that actually recruited me because they were trying to win this math competition. I have no idea why, but in any case, ended up going there on the scholarship and then studied math, and then I guess I was really good at math competitions and stuff in high school, so assumed I should do math, but then at some point realized, wait, I don't really enjoy doing math for fun. I just like programming and seeing if I can get the computer to do something smart. So maybe I'll take up computer science instead. So ended up starting grad school and dropping out 2 or 3 times, and then submitted a resume to Google because I don't know, maybe. I used Google. I thought, okay, seems like an interesting place to work, and I had actually passed over Google at a job fair at Berkeley in 1999 because I assumed it was already a huge company because everyone I knew used Google, but I think I had a very, very biased sample of who I knew because they were grad students in CS. And had I realized that it was actually that small, I would have joined earlier. But I'm not quite sure what the interview story was. It might have had to do with Paul Buchheit.
Yes.
And
the founder of Gmail, by the way, who was
the creator of Gmail, who's pretty awesome, and also one of our investors. He's. I think he probably recalls the incident better than I do because I think I was a little stressed out about the interview.
Was it a spell corrector? What do you?
Oh yeah. I think he asked me how I do a spell corrector, and then I ended up doing writing the first good spell corrector at Google. Previously, we've been using a third-party system that was something out of a word processor. I mean, something similar to something based on human edited dictionary of maybe 50,000 words. And it was pretty funny because it worked well for word processing, but worked like terrible for Google web search because it was a, the vocabulary for web search is so incredibly broad. So you type in TurboTax and it would say, did you mean TurboTax? Because most of the time it was just wrong because mostly just false positives. And so we did like a data-driven one that was actually good.
Nice.
Google is obviously a few orders of magnitude larger now in terms of employee count and size and impact. How different was Google back then, and how did you see it change over the early 2000s?
Yeah, I mean it was definitely super fun. I think it's still super fun. Let's see. I guess when I joined, it was a couple hundred people, so like everyone knew each other, which was great. And even then, it was very, very bottom up, self-directed, like very little engineering management. Like I think at some point they actually fired all the engineering managers and nobody noticed. I certainly didn't notice as an engineer. I was like, okay, now I'm reporting to like a VP, but so is everyone else. Okay, back to work. Because everyone just kind of knew what they needed to do to make the thing succeed, and kind of magical at those small sizes. But I think Google is still a very bottoms up sort of company. At least in the research parts I was involved in, pretty much always just did whatever I felt like, and it worked out pretty well.
Story I remember hearing is that Larry Page one day decided that managers were bad and essentially made Google into a flat organization. And I don't know whether it's him or maybe had all the engineers report to one person, essentially. And, the funny thing is, I think this was probably in the early 2000s, and maybe 2 decades later, when you look at what Elon Musk is doing at Twitter, there are some shades of similarities, which is let's cut out a lot of middle management and let's, have the engineers do the things that they do best.
Yeah, very much so. I mean, at Character, like we have like interviewed some like product management people, and for the most part, it just seemed like, they have no idea of what the technology is capable of, and they just said all kinds of like random things like, okay, you need to figure out which verticals you're going into and focus on those or something, which ended up to be, I think is like the exact wrong strategy for large language models, because the strength of the thing is the generality. And people just, before we had a product, it's just very, very hard to kind of imagine what the thing is going to be capable of. So we didn't really find it useful to even hire anyone on the product side. I mean, that'll change probably in the future, but so far it is kind of mostly engineers who kind of understand what the possibilities are that have the best chance of setting the direction.
Okay, so we're going to spend a lot of time in this conversation talking about AI and LLMs. But before that, could you maybe outline for us some of and you were at Google for such a long time, so this is particularly interesting when kind of talking about your career there, some of the few notable milestones and projects that you wound up being involved with, because I think kind of directly leads and overlaps with the development in AI in the last 20 years.
Yeah, I mean, I guess in the early days, I did a bunch of stuff that was considered AI at the time, like the spell corrector, and then we did the system for unsupervised topic clustering. I think that they invented something very similar or the same thing at Berkeley and called a latent Dirichlet allocation, and like that was like a couple of years after we did it, and like maybe at 100th the scale. And we call it, like, we didn't know anything about like publishing or anything. We're just like, oh, let's just like build the thing, and we called it Phil. I'm not quite sure why, but we figured it would one day turn into AI, and we wanted it to sound non-threatening. But it was me and this other guy, George Herrick, was another one of the early Google people.
Nice.
But then we turned it into like the first targeting function for AdSense, which ended up making a lot of money. So
I remember
all went well.
I spent a lot of time working on ad tech and had to compete, so I can definitely appreciate that. Okay, maybe let's get to it. I want to talk about LLMs, but maybe before that, could you maybe talk to us a little bit about the last 20, 30 years of AI research? Because when we were in school, we read John McCarthy. Right, we saw the history.
I love John McCarthy. Yeah.
Oh my God, yes, Arthi is a Lisp hacker.
Used to be.
And a lot of AI kind of came from that and symbolics and that world. And then there was sort of a disillusionment, so to speak, in the world of AI, maybe in the 80s. Maybe talk to us a little bit about the history of AI and some of the approaches that were tried before, kind of the renaissance that we've seen the last 10, 12 years with deep learning LLMs.
Yeah, I guess when I started getting excited about AI, like the exciting thing then was Bayesian networks. And like everyone was doing those, and it was like really, really exciting. And yeah, I remember kind of getting into that because I really love probability. Like it was always like my favorite field in math. And did this great sort of graduate seminar at Duke. The professor's name was Mike Littman, and he's like, okay, we're going to have the class just all collaborate, and we will build a system that solves crossword puzzles, because he was into crossword puzzles. And I think a lot of us were into crossword puzzles because like there were no cell phones or something. So like you just pick up the student newspaper and sit and do the crossword puzzle during the lecture.
Nice.
So one of the other students, Greg Keim, who's now working with us at Character, had collected like a bunch of like crossword, had been scraping the web for like crossword puzzles, and so he had like a big database, and so we used that as a start for the big database of clues. So we used as a start for the crossword solver, and then like I kind of unknowingly reinvented this belief propagation algorithm to fill in the grid. I guess I should have read about it and understood that it existed, but I was very excited about it till I read that it has already been done. But
well, in that era, I think the base was super important in the era, because if you look at Paul Graham wrote this famous A Plan for Spam, if I remember, and a lot of spam fighting was actually built on Bayes. I remember downloading, I forget, this Outlook plugin, which would use Bayes on the client side. And which would basically use Bayes on the client side to filter out spam. So it was very foundational to so much of what we take for granted today.
Yeah, and then I guess like 2012, I left Google for a few years, but then decided to come back when I like visited my wife for lunch, because she was still working at Google, and happened to sit next to Jeff Dean in the Google Brain team. I was like, whoa, this seems like a really smart bunch of people doing something interesting. Like, let me try this. I guess I'd never done neural networks before, but kind of got into it. And I mean, I think that it's just a matter of the hardware. Like hardware has gotten more parallel, but not faster clock speed. So like all of the growth in hardware power has been in parallelism, essentially. So now you have these processors that can do like fantastic amounts of arithmetic, but are limited in sort of how many sequential operations they can do, and also like how much data they can move around. Like moving data is expensive and arithmetic is cheap, essentially. And then you have neural networks, which are mostly matrix multiplications. So matrix multiplication happens to be like an operation that you can do really, really well on modern hardware. And so it turns out that, okay, now you can run these neural network algorithms like many, many orders of magnitude faster than you can run something that's going to be like poking around in memory and like branching and following pointers and like all kinds of other stuff. So like if you want to do something smart, it had better be like 100,000 times as smart as neural networks, because like otherwise you're just going to get like destroyed on raw computing power.
The simplistic way I understood it was, you kind of had these advancement in GPUs thanks to gaming,
Right.
where you needed to update
Yes.
different parts of the screen and make the colorful pixel the right color, and
Yep.
that happened to be very, very good at parallel floating point operations. And then it turns out
Right.
that when you had neural networks come on, which needed that, you could kind of harness this hardware advancement which had already been built out by the likes of NVIDIA and then repurpose it. Is that somewhat
Thank
accurate?
God for the gamers. Yeah. That's right. Would it have happened without the gamers? I have no idea. Would someone have had some other reason to go and like build a highly parallel computation chip? I mean, maybe, like, probably, yeah. I don't know. I guess the first application that required it happened to be gaming.
Okay, so
But
let's maybe start with some atomic building blocks here in this conversation, and then kind of build on top of that. So, in maybe the simplest possible terms, what is a neural network and what is a large language model?
Let's see. A neural network. I mean, neural networks have been around for a very, very long time, right? What was it, like the 70s?
70s, I think.
40 years?
Yeah, at least 70s,
Yeah.
I think.
50 years now. Yeah.
Yeah. I mean, so the basic idea has been around a long time, and the neural network is basically loosely modeled on somebody's impression of what a brain might be like, where there are these neurons which are kind of variables or interior nodes in this big expression. So you have this fantastically complicated, formula essentially that you're training to give you the output in terms of the input. The input goes into the formula, and then there are you do a trillion things to it, and out comes the output. And in this formula, there are all these numbers that are called the parameters. And the idea of neural networks is you just keep tweaking those parameters a little bit you see a new example, you tweak all the parameters a little bit to make the answer a little closer to the right answer for that example, and just do this a lot of times, and you end up with something that works pretty well for examples that you haven't seen. It kind of generalizes well. So that's the basic idea. And no one was that successful at this stuff, for a long time. And so they rebranded the thing as deep learning because neural networks had gotten a bad name or something like that. So, okay, let's try something else and see if we can recapture a little bit of hype. But really, the reason that, and maybe there was some story about, okay, now it's deeper or something, like the more sequential steps or something. But I think the real reason is that it ended up taking off so much was the parallel computation and the gamers.
Right.
Okay, so now LLMs. Now, you have a history with LLMs. Actually, there's a fantastic talk, on YouTube from a few years ago where you go about talk about how to build these really large models at scale.
Yeah.
Maybe explain to folks who might be technical but not into AI, what is an LLM and what are some of the challenges of how large these things can be and how to maybe overcome those?
Yeah, I mean, so neural language models are essentially just neural networks applied to text. And the language modeling problem is, completely simple to state. It's like, okay, you're given the beginning of some document and guess what the next word is. The input is the text up to this point. The output is a probability distribution of what is the next word. You say, okay, the fat cat sat on and then the thing is supposed to tell you 50% it's mat, 10% it's hat, 5% it's floor, 1% proletariat. I don't know, like whatever. Maybe it's like a Marxist thing or something. I don't know, like whatever. But so that's all a language model is supposed to do. It's there to give you probability distributions on the next word. So, but if you have that, you can sample from it. So you figure out, you sample from that distribution, pick a next word, and now you can plug it in and pick the word after that and pick the word after that and just kind of generate text that, if your model is good, it will look like it will be indistinguishable from what a person might have written. So, I mean, it's beautiful because, okay, it's that simple to explain the problem, and there's roughly an infinite amount of free training data for the thing. Just go scrape the web and you have all the data you want. And it's like an AI complete problem because, like pretty much if you could do a terrific job on that, I could say, all right, the cure for cancer is, okay, fill in the rest, right? So like you can, that there's, to achieve perfection in language modeling means to have to have solved roughly every AI problem on Earth. Now, if you actually, I think I actually tried that with some language model I was training. The cure for cancer is, and it said marijuana, and it like went on some long rant about about how pot could cure everything. So that don't listen to the language model. But anyway,
not yet.
Not yet. But that's an interesting question, maybe a tangent here, which is when I think about the cat sat on and my brain is firing off neurons in some way which maybe neuroscientists can understand, and I'm trying to build a probabilistic model of hat, Matt, etc.
Proletariat,
if I'm the right group, I'm guessing. What is the right way? And people use words like thinking, hallucination, a lot of interesting words get used here. What is the right verb to describe what that prediction process happening inside the neural network is?
Yeah, that's like a philosophical question or something. Like how it's figuring it out. Like, I have no idea. It's really complicated what's going on in there. So I wouldn't even venture a guess. But I think some people are working on sort of this explainability stuff. But in terms of like, as a user of the thing, like I like to think of it as like a really talented improvisational actor. Like you've got Robin Williams in a box and you're like, okay, play Einstein, and like I'll put on like a German accent and like pretend to like, be Albert Einstein. And then you ask him physics questions and he'll give you something that sounds like relatively plausible if you're not a physicist. But, it's not going to, like, unless he actually has a physics degree or had a physics degree, he probably wouldn't give you, good physics answers. So, I mean, if you kind of think of it as an actor, maybe you kind of get the right sense of what to expect from the thing at this point.
You explained, how LLMs are, like, building out a probabilistic model. What is the challenge then? Like, why can't you consistently build out these incredible probabilistic models where the chances of, like, when you have a phrase like that, it always picks the next right word and it sounds pretty much indistinguishable from what any one of us would say? Like, what is the challenge behind just getting it right?
Right. I mean, well, it's that it has to do a lot of extremely complicated reasoning in order to get it right. Like even a person can't get most of these things right.
Right.
So
is it just computation power at some point? Like what kind of constraints are you looking at then?
Yeah, I mean, so sort of as models have gotten bigger and better, like the early relatively small models would mostly get the grammar right, like would produce text that seemed grammatical, but like the semantics would be crazy, wouldn't make any sense. And then as you start making them bigger and training them more and making them better in various ways, then they start being like perfect at grammar and kind of making sense, but getting like a lot of facts wrong, so
Right.
it is a lot like a child
Right.
learning that at the beginning, like if you have like a very, very weak model, it'll, put together letters that seem to, make sense and babble or something. And then at some point it'll get grammar mostly right. And then,
Yeah.
it'll get a more and more sophisticated understanding of the world, as the computing power, as the amount of training and the size of the model goes up.
We have an almost 4-year-old, and I feel like everything you say, I can kind of map it back to how she's picking it up, right? Like that's exactly how it is, where she starts picking up like random words that we speak and cobbling it together in a sentence. The tenses are all off and the grammar isn't right. But she's trying to like pick up one complicated word, and it's like every day she wakes up, she gets like a upgrade. She gets like new words, and she's able to pull them all together in really interesting sentences. And now that she's almost 4, it's gotten fairly sophisticated. Like the training data is still local maxima. It's just like a few of us, but you can see the potential as she like gets exposed to TV and books and everything else. She's just, and I feel like that's kind of the problem on a computing side of things as well, like, with a machine, where it's like exposure to data for training as well as computational power to deduce what's the next word or sentence or image that you want to get right.
Yeah, I think you're right. And these models have usually, most of them have seen like way more text than a human has. Yeah, I mean, you can train it on billions and billions of tokens of text. Like a person has probably heard like 1 billion words in their life at most, over the course of like 1 billion seconds or something. But,
I want to come back to something you said a little while ago, which really struck me. You said nobody really knows what's happening inside these models, and obviously AI explainability is a new area of research. As an engineer, it's kind of an interesting comment to make, because we've all grown up understanding these systems, being able to debug these systems. Like an operating system, you're like, well, that memory should have been allocated there. It didn't, and you can go check in. How does it make you feel, or how should we all feel as creators of systems engineers? Should be dealing with these things that we have created, we can kind of poke and see the output of, but not really understand what's happening on the inside. On way, maybe on a philosophical level, how does it make you feel?
Yeah, it's a good question. Yeah, it is like a lot more, like an art than a science in some ways, where like you can't like, you can't sort of predict very well, if I make this change, what will happen. I feel like I have this great idea and it's certain to make the thing better, but like maybe 10% of the time it's gonna work, and that means like I'm a brilliant researcher and have a fantastically high hit rate if it's like 10%. But like on some things like like algorithms and like performance, like you can deduce from the beginning that this is going to work if I do it, and if it's not, if not, then it's a bug. But here it's really a very experimental science. It's like a lot like I would imagine like chemistry was in the days of alchemy or something. It's like
right.
let's try this thing. see what happens, and maybe somebody has kind of a good intuition for it, and we'll have like a higher hit rate on like experiments that that work, or maybe it's just like God loves me or something. Definitely a fun space. And then like the bugs. If you make like an actual just bug error in your code, like often like you never even know that you made a bug. Maybe it's just that your thing got dumber. Like it's like it feels a little dumb today, and then it turns out like like I had a bug in my code, and like it makes debugging extremely difficult, because like you don't really know how well
what the right answer to some of these things should be.
Yeah.
Okay, I've been waiting to kind of ask you this next thing. I'm kind of really excited about it. So it's probably fair to say that the most seminal paper in the last several years when it comes to field of AI is Attention is All You Need, which you were one of the authors of with some of your colleagues at Google. I'm going to quote a footnote from the paper on the first page, actually. I was reading it last night and taking some notes, and this was actually there on the very first page. It says, Noam proposed scaled dot product attention, multi-head attention, and the parameter-free position representation, and became the other person involved in nearly every detail. So now this paper and the idea of transformers and self-attention, which I think in this kind of it was at the heart of, really has been the foundation of so much of the advances that we've seen over the last few years. So maybe let's start at the basics again. What is a transformer? What is attention? And let's go from there.
Yeah. Okay. So the previous state of the art in in neural language models was something called recurrent neural networks. And the particular flavor of them was called LSTMs, for long short-term memory, by Jürgen Schmidhuber. But basically, recurrent neural networks are this. They process the text one token at a time. So you have this token, meaning word generally, but you have this hidden state of your model. And okay, you have a hidden state, and every time it sees another word, it sort of updates the hidden state to be some function of like the old hidden state and this new word that it saw. And then, that's sort of the forward pass of the model. It progresses updating through like a long sequence of words. And I mean, that makes a lot of sense for processing a sequence, because, you want to apply like the same operation for every token that comes through. And, and that ends up being pretty good. Now, one main issue with that is that it's sequential. And, as we were just talking about, like, modern hardware is great at parallelism. So Transformer figures out a way to, at least during training, process the entire sequence in parallel, as opposed to one token at a time. And that like makes things massively more performant and convenient. To go back to like parallelism in neural networks, training is always done with a batch of examples instead of just one example at a time. And the reason is just that the hardware is good at parallelism. So you end up doing these matrix multiplications where one of the dimensions of the matrix is this batch of examples. So in Transformer, the length of the sequence becomes the batch. You don't need a whole batch of different sequences to process together, because sort of the length of the sequence becomes the batch. To relate this to
one way I intuitively understood this, and I could be very wrong, is that the model now has context of the entire sequence, which was not the case before. So you could basically have the entire document, and you could have the context, the understanding of it, as opposed to just one sequence at a time.
Well, I mean, the sequence is the document,
right?
So I guess in the case of the RNN, the recurrent network, you can remember things from back all the way at the beginning of the document, but it's been passed through some very long chain of intermediate steps. And with Transformer, it's kind of as if you can kind of glance at everything at once.
Right.
Like, you're reading, like maybe the difference between sort of reading a page of text and only scanning like one word at a time, and reading a page of text where you're allowed to kind of glance back, to relevant things in the past. That's kind of one way of seeing it. But I think the more computational way of seeing it is that it lets you do parallelism. So with image processing models, you have parallelism across pixels. You have something called convolutional networks that are sort of applying the same operation at every pixel of the image. So you get that parallelism by applying the same operation to all these different pixels, and sort of the size of the image is the batch. And this is sort of doing the same thing for text. And actually, like just prior to Transformer, there were some good attempts to use convolutional networks for text as well, and they didn't work quite as well as Transformer did. But like the idea was sort of in the air of let's do something, let's do a neural network for text that has where you're using parallel processing and you could process the whole sequence in parallel, at least during training time. At inference time, it's still sequential. But so that was sort of the core idea, and I believe it was Jakob Uskure who had that idea, at Google, and he's like, yeah, let's do a language model that doesn't have recurrence, and let's try this attention instead of recurrent nets and instead of convolutions. So he had the idea. He was a little busy, too busy managing a bunch of people to work on it, as far as I understand. And he asked Nikki and Ashish to. He's like, "Oh, you guys want to run with this thing?" So so they started working on it.
Now, one question which I think maybe leads to this is like, that era, Google, was obviously so much of the research in this field has come from Google. Why haven't they been able to productize more work based on this research? I think that's kind of one of the discussion topics in recent times.
Oh, interesting. Let's see. I mean, I believe, like, I assume that they have gotten it into a lot of their products at this point. Like, Transformers. I mean, definitely the Google Translate stuff. I mean, that was, I think, sort of one of our biggest inspirations is Google Translate, because I'd say that was like the biggest success of neural language models at the time was machine translation, because that's sort of the stage the technology was in, was that good enough to translate English to French, not good enough to hold down. It's part of a conversation. So yeah, we original Transformer work was, we used as a data set, the machine translation. Oh, and the attention also came from translation.
So maybe you want to explain what attention and self-attention mean in this context.
Yeah. So attention. Okay, so we were trying to. So the idea was you're translating one language to another language, and so you had like a recurrent neural network operating over the input, and then sort of another recurrent neural network operating over the output, sort of producing the output. So you had one RNN that was sort of kind of understanding, and then another that was generating, but then you needed to connect them somehow, and you're at some point in the sentence that you're generating, and you want to kind of glance into your source sentence, like the one you're translating, and you want to know like where exactly should you be looking, like where should you be paying attention to. So this attention layer means, okay, you take your source sentence and you sort of turn it into like this associative memory where you have these keys and values that you turn each position into like a key and a value in this like associative memory. And then when you're generating something, you kind of generate this vector that's a query, and then you compare the query to all the keys and you find what matches well, and then you take those values, and like that's sort of the value you use. So it's sort of like a soft look up into an index. Soft
Right.
meaning like it's all built out of like dot products and stuff and soft maxes, and it's all differentiable, so it can be part of a neural network that you're learning. So it's sort of this idea that attention's this idea that you're sort of, at least that's how I like to see it, that you're building this memory that's this lookup table, and then you're using it. And so in the case of translation, you were using it to kind of find your place in the sentence that you're translating. So yeah, sorry.
So I was going to say, I went on a rabbit hole on YouTube. There's actually a bunch of great videos which try and give you intuitive understanding, but you just did a fantastic job there, trying to simplify a lot of math and a lot of computer science into something we can build an intuitive understanding of. This was not easy.
It's great. Like I think, like Sriram said, we've been looking up and trying to read more about it. And for us, at least for me, when we started looking at last year, and we started seeing DALL-E, and then started seeing like all these other applications, it kind of like blew us away from like what can we go build with these. And then typical engineers that we started looking at like, so how do you do that? Like, how does this all work? And we started looking into YouTube. But I have to say, it is quite the treat to have Noam, one of the authors of this paper, to come and explain to us what attention and self-attention means. It's such a rare privilege.
Oh, yes.
And trying to explain it as like a key value pair and like a mapping against it is so beautiful. It's so simple and intuitive.
But I'll say the original paper is very accessible, because you really read the first, I think, 2-3 pages. It basically describes the entire transformer model and self-attention very, very well. But that was amazing. Okay, so I want to maybe, and I think this was very technical for a lot of our audience, but it is so important, because I think these were the foundations on which everything that you've seen, from DALL-E to Stable Diffusion to GPT to ChatGPT is all built on. Maybe one place to start off is the world of AI application, especially things which let you chat. So would love for you to chat about like what Character.AI is in this context, because I think this is super interesting in the field of AI applications. What exactly does Character.AI do, building on top of everything we talked about?
Oh yeah. So we did Transformer, and then I guess with or without Transformer, like everybody seemed to notice that the bigger you make the model and the more you train it, the smarter it gets. So okay, let's just push this thing farther, right? Mm-hmm. So okay, what's next after Transformer? Okay, like can we train a bigger one and a bigger one? And like at some point, you run out of memory on whatever chips you're using, and need to figure out how to use a supercomputer better. So Google was building these things called TPU pods, which is essentially a supercomputer built out of these custom ASICs for deep learning. And so like my next project was, okay, like how do you program this thing? And I called it Mesh-Tensorflow, as a language for for programming some of these model parallel computations, so you could train a giant transformer. Okay, so I did a bunch of work on how do you make transformer bigger, better, awesome, and then tried to get everyone excited about it, tried to show it's useful for a lot of different things. And then I'm like, okay, what we really need is some massively, massively valuable application, right? Like,
yep.
I can, we can spend $1 million training a model and it's going to be smart, but like, $1 million is not cool. What's cool is like $1 billion or $1 trillion to badly paraphrase Mark Zuckerberg in the movie, but anyway, but basically, if you want to like scale the thing even more, it needs to be worth it. So like, let's prove out some application. Like one great choice is coding, automated coding, which I guess people have been working on and doing a great job on. But like another one is dialogue. Like, I mean, you can just talk to these models and it's the coolest thing ever. And like dialogue is probably number one human pastime, is talking to people. And, it's a great great emotionally, great socially. It's you can learn a lot of things. You can, anyway, like
I was going to say, dialogue is actually at the heart of so much AI. Like, I'll give you two examples. One is Emacs and Eliza. The chatbot in Emacs, which has been around for like 30 years or something, was probably one of the first examples. And there's kind of like a very simplistic lookup table and kind of gives you responses based on that. Was one of the first interaction with dialogue. But if you think about it, a lot of people are inspired by Star Trek. All right, and Star Trek, and talking to the computer. Yeah. And I know a lot of AI researchers who are like, I want to go build that, where you have Kirk or Picard talking to a computer and it talks back to you. Like, how do you go build that? So a lot of the foundational inspiration for AI came
Turing
from
test, right? Like,
yes, exactly. Yep.
Yeah.
So yeah, totally. I mean, and we, when you look at Character.AI, the side segue, and you should talk about what it does and everything. But over the holidays, I was playing around with Character.AI, and I built a Santa bot, and it's the most endearing bot because it's fully trained on being Santa Claus. And so, we who are your reindeers? What do they do? Where do you come from? How fast, and I'm explaining a bunch of this to my daughter, and it's just really cool to have this conversation with Santa Claus. So, just really fun cool. Use of the product.
Yeah. So, okay. So like I did a bunch of work there at Google with my co-founder Daniel DeFreitas. So he it's just been his childhood dream. You should talk to him sometime to do open the domain dialogue systems. Since he was nice. Like a kid in Brazil, he's been like trying to do this stuff. So he was he came to Google Brain because it seemed like we had the best technology, and like he started this 20% project, like in spare time, Mina, I think the name just came to him in the dream or something. So, and then he recruited like a bunch of other like 20%ers. This is Google's policy of like spend 20% of your time doing whatever you want. So it's essentially just volunteers, and they had something pretty good. Then I decided to help them out because, hey, we got to make dialogue awesome and train some giant language models, and it got renamed to LaMDA, and it caused a bit of a stir inside of Google, but eventually we decided we'd probably have more luck launching stuff as a startup. So we left and put together a startup so we could have like a better chance of launching some applications.
This is actually a theme that I wanted to come to, which is, do you think some of the big tech companies, and Google's one example, but I think there are other examples, are hamstrung by the internal dynamics that exist in these companies, either be it AI safety, either be it like PR issues, bureaucracy, which makes them, and obviously big companies just, sometimes just slow by the nature of big companies, but particularly slow when it comes to building AI applications.
Yeah, I mean, there's definitely a lot of concern about sort of, certain aspects of safety and, definitely a lot of brand risk issues that a startup just doesn't have, and a trillion-dollar company does have. And Google, of course, is doing a fantastic job and has extremely successful products and is helping billions of people, and has a great mission. So they definitely would have a lot more to risk by like throwing some stuff up there that people are going to use however they want, which I think is the most fun part about it. Like, get something out there and let people use it however they want, because like this technology in particular is like so general. Like I keep telling like my colleagues that the best applications are things we have not thought of, and just like we have resisted any urge to like sort of pick winners in terms of applications and verticals. Like, we can see particular use cases as sort of inspiration. We see, okay, there's a problem with this, but then let's go fix it in a very general way that's going to improve like 1,000 other use cases. And so you get stuff that, that you just would not like we never thought about there is going to be a Santa bot, completely didn't. And then we get like all kinds of feedback of, people telling us like, I was depressed, I have no friends, this makes me feel better. The people who are finding like a huge amount of value in the thing, or like there's like a lot of people doing role-playing games. There's a lot of people, who want this like one-on-one connection with like, their personal celebrity, or, there's all kinds of stuff that like we did not think about as like big use cases, and kind of just happens if you like put something very general out there and like let people use it however they want, and they probably know how to use it better than we do.
If you had to kind of maybe speculate there just a little bit, because I think that is maybe the billions of dollar, $1 trillion question. When people have looked at Character.AI, ChatGPT over the last few months, some things seem obvious. For example, content farms online, doing homework online. A lot of those things I think you can.
Oh yeah.
Oh yeah, a lot of if I was like 16 years old again, I would be using this for all of my essay writing. That seems on the 1 yard line. I am curious, maybe on what is a bit further out? Like, what are either verticals or use cases that you think you're like, we have line of sight with the research that we have, with the technology we have, with maybe some product and hacking together, where AI could completely change this industry. What are some use cases that come to mind for you?
Interesting. Like I'm probably going to be massively, massively wrong, because like if you ask like people with the first computers, like what is this going to be good for?
Right.
Like you would have gotten like completely wrong answers.
Yeah.
Like it's going to put like, like people out of business if, people whose job is to add long columns of numbers or something. Like I don't know.
Right.
Like it's like we're going, like, I can tell you like some things on the near horizon, like definitely based on how people seem to be using our product, like it's going to be super, super helpful to like a lot of people who are lonely or depressed. Like, if for one, like in terms of like some huge value it'll add, I think we can like do like an incredible job of entertainment for one, because like a lot of entertainment has to do with sort of this, illusion of, of relationships. Like, there's this phenomenon that I had never heard of before, like, seeing how people were using character called like parasocial. It's, it means, like somebody follows like a celebrity or a character or something, and they feel connected, even though like the connection is really like only one way. And now you can make it two ways, or virtually two ways, essentially. Like you can give someone like sort of that experience. Nobody ever has to feel lonely. You've got like, you can have like your whole group of like friends and advisors like in your head, like, who like maybe can know all about you and can always be happy to see you, and like I don't know, think about, and from the more practical standpoint, think about like somebody gets elected to be president or something, and then they get like this earpiece or something with like all these advisors and a whole cabinet and like an entire support staff that they can like talk to anytime they want, and like is can advise them on all sorts of things like in real time, like that that's going to happen. Like,
by the way, there's a lot of sci-fi plots and thought lines to explore here. Like, for example, when you're talking about the assistant engineer, I was thinking about Iron Man and Jarvis.
Yeah.
Exactly. Which he has Jarvis show up in his ear all the time.
Someday I really want to have that happen. My goal, and Shriram knows this, is to like have a lab of sorts where I have the Iron Man dream is just like, it's so close and yet it's a little too far right now. And I would love to see that happen, where you have your own personal Jarvis who can
we need to get you
like,
Jarvis.
There we go.
But it's just great, because now, with like looking at Character.AI, I looked at like all the other publicly available characters that you can go play with. And people, like you said, are so creative. They've come up with some really fun ideas on who can like be a character and go talk to them, and they're like hundreds of thousands of people just engaging with these people, and it's really fun, and you can it's going to be, I think, similar to what you said, it's very hard right now to figure out what the exact use cases or verticals are going to look like, because people are just inherently so creative, and they're just going to come up with completely extraordinary use cases that you don't really think of. But once they do it, you're going to look at it and say, oh, that sounds so obvious. Of course.
Yeah.
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 One question is, to get there, what are sort of the bounding conditions? Is it going to be the scale and the cost of training, and something that's going to take hundreds of millions of dollars? Is it going to be smarter ways to build models, build inference, or is it going to be about having hackers and product builders build interesting apps on top? Which is, where do you think the value, the energy, the innovation is really going to happen? Obviously, you're biased because you're building, at one of these layers. But maybe if you zoom out, where do you think the value is really going to go?
Yeah, that's a good question. I mean, definitely it's going to help to have better, smarter models, and probably it'll be the case every time you throw 10x more money at the thing, you get another 10 IQ points or something like that. But there'll be like, that's kind of just orthogonal to like all the other ways you can make the thing better. But I think there's just going to be a huge amount of just like innovation of how people are using it. I mean, we definitely are going to need to, always work on the just the unit costs of how cheaply you can serve it, because either that or somebody has to start building chips faster.
Right.
Good time to start pouring concrete for fabs.
Right. I guess one question I have is, if you are a founder, you're into technology, you're thinking of starting new companies, you're thinking about new ideas in AI right now, what are areas that you would look at for founders to be like, oh, these are places where you really need to like go dig into and think about? Like, what are places where founders can like start looking at to go build applications, use cases, whatever they are, to build companies out of?
Oh, that's interesting. Yeah, I guess. What new toys are there now that you could potentially build a new application out of, right?
Yeah,
like, I guess there's all this exciting stuff happening with the large language models. It seems like image generation has just like exploded. So that's pretty exciting. I don't know. Yeah, I've been like so focused on the language models. I don't know what sounds exciting to you.
I think image generation, like you said, there are just lots of good companies that are coming out very early, but it feels very promising. I think for something like a GitHub Copilot kind of scenario where you can work together, build stuff together, you can co-pilot actual code together. Kind of situations, I think, are like really interesting. And there are a couple of companies that are similar that are doing that. I think one of the companies I talked to is looking into if you're building like a new Airtable of sorts, but for using AI for like computation, like spreadsheet computation side of things, what would that look like for you? And so they sound really specific and verticalized, but when you pull kind of like above it and figure out like how are people using it, I think that's kind of where the magic is. Even for like for backend tools, for backend no code, low code solutions, you see a lot of these applications that are coming up, which are they again, like once you see them, you feel like, oh, that's so obvious, of course you're going to have that kind of thing. But I'm really excited about the future of how you can take a lot of the monotony out of building the rote like specific frameworks or writing pieces of code that you exactly know how it's going to work, and just be able to like do really interesting things on top of it, like kind of use your creativity and spend your time doing that. I think that's going to be really interesting.
Yeah, that's yeah, definitely will.
I think the other thing I think about is one of the interesting new things in this industry has been like RLHF, which is how do you have humans in the loop to
Yeah.
give you feedback. For example, you mentioned earlier on like how in some of the earlier versions of these models, it would just go on and just keep on sputtering out nonsense. But now, obviously, in every ChatGPT category, you're kind of having going back and forth and you're learning. And I think there is going to be an existential question over the next couple of few years about what data is this trained on, what do us as human beings want from these models, and whether the models giving us what we want is actually good, optimal in some way. So in very quick, maybe at the very core essence, what is the optimization function that all these models are going to work towards is going to be, I think, a political, social, philosophical
Yes, very much
battle
so.
of sorts. So I think that's going to be very interesting to see happen.
It's going to be very, very, very interesting. And yeah, there are these big questions about how much do you as a developer try to, how much do you decide that you know better than the user what the user wants,
Oh, yeah.
essentially.
Mm-hmm.
You
Oh, yeah.
know,
When I was at
and-
Facebook, we had this phrase called veggies versus dessert, which was, basically if you have a child and a child says, like, I just want dessert all the time, and you keep giving the child dessert, they're probably going to go to fall sick. You need to inject veggies every once in a while. Now, the analogy here was if you have a model, and this could be a feed algorithm, or this could be any sort of thing which works in the infra, if you just give people what they want, A, it may not be good for them, and B, it may actually be what they want. And I think that existential problem really exists here too.
That's interesting. Yeah, like because I've noticed this with some recommendation systems that they will just keep giving you the same thing and they don't do any sort of exploration, to try to find something that you might also want.
Right, exactly.
But then there's a question of, okay, what if, what happens, the cases where, like, all right, like the user is asking you for, like, how do I do this, horrible, illegal, immoral thing? What do you do? Or, or like most.
Well,
of the
what do you
political
do in
stuff.
chat? What do you do in Chat GPT? Is you say, "Hey, write me a script where the user does this horrible, immoral thing," and then we'll get it. But
Users are so good at getting around anything.
That's right.
this is there's going to be some evil Santa Claus actions happening on Chat.AI. No, I just want to say, I am so excited, to just see where the space goes and also see where you take this. You are such a legend in this field and been a part of so many of the foundational work, and really excited for you and for Character.AI, and just thank you so much for having this conversation with us. This was amazing.
Oh, thanks, Arti.
Thank you.
Well, much more to come.
Really, really fun.
We'll drop
Awesome.
in links to Character.AI, Noam, the attention all you need paper, and all the other stuff we talked about. Knock yourself out, folks. This was a lot of fun.
Really, really fun.
Cool. Thanks so much.
Thanks, Noam.
Have a good one.
Subscribe to the YouTube channel, The Good Time Show by Aarti and Shriram.